Welcome to my Switching, Routing, and Wireless Essentials course. This should be the CCNA version 7 curriculum. This is the second of 3 courses. Welcome to Switching, Routing, and Wireless Essentials version 7. This is module 14, Routing Concepts. So what are we going to be covering in this course? We're going to be looking at path determination, how the routers actually route. We're going to review a basic configuration of a router. We're going to examine an IP routing table, and we're going to look at static and dynamic routing protocols. So let's go ahead, let's jump into our path determination. So essentially, a router will receive a packet, and it needs to determine how to forward that packet. What interface should that packet go out of? The process of figuring that out is known as routing. Typically, a router will have an ingress and egress port or interface, but that's not always the case. The primary function of a router is to determine the best path to forward packets based off of the information in its routing table. Essentially, it will be forwarding the packet towards their destination using the routing table. The route table can be learned through static or dynamically learned information, and we're going to get to that in a later section of this. So let's look at an example. Here we have one LAN and another LAN. If we have a person over here, they will send the packet to the default gateway, the router. The router will look at the packet and figure out how to process it. The router has to know what port to send information. If it knows that this LAN is connected to this router and this router is off of that interface, that's what it will do. It will forward that packet out this interface so that this router can receive it and then process it along. This is what the route table would look like. And you'll see here it has a statically configured route, 2 directly connected routes, and we have that S-learned route. That S-learned route will be sending anything out that interface destined for that network. So this router will go, okay, I need to send a packet to that network. Send it to that IP address, which that's going to be that guy right there. As this information grows, if we had multiple routers, it would do the same thing, except it would be the next hop. Here we only have the 2 routers, so we have that pretty simple. So the best path will normally equal the longest match. And the best path is basically the route in the routing table, and that's called the longest match. The routing table will contain route entries consisting of a prefix, the network address, and the prefix length, the subnet. For there to be a match between the destination IP address of a packet and a route in the routing table, a minimum number of far left bits, network bits, must match between the destination and the destination IP and the destination network. The longest match is the route in the routing table that has the greatest number of far left matching bits for the destination. Basically, the greater number of network bits that match the destination IP and the destination network, that will be the longest match. The term prefix length will be used to refer to the network portion of the host bits for both IPv4 and IPv6 throughout the remaining Cisco courses. So let's look at an example. Here we have the destination IP, and we have 3 route entries. So we're going to be looking to see which route entry has the most matching bits. And that's going to be, you'll notice route 1 has this many, has 12, where route 2 has 18 matching bits. Route 3 has 26 matching bits. This will be the route, the longest match for that IP address. So it will then use this route to forward the packet destined for that network. If we're talking IPv6, again, we're doing the exact same thing. We're breaking down the host bits, and we're seeing which ones match. Here we have 40 bits, 48 bits, and 64 bits, but you'll notice the 64 bits does not match. So we're going to be looking at the 48 bits. Those will be the ones that do match. Again, here we have the 48 bits that do match, but then between 48 and that 64, we have 5555, and those ones do not line up to the destination. So that route does not count. So the longest match is route entry 2 because of the 48 bits that do line up. So building the routing table, we have a few different things that are tied to the routing table. Directly connected networks are added to the routing table when the local interface is configured with an address and is active. Those are going to be the C and L networks. We have remote networks that are not directly connected to the router, and the router will learn about these in one of two ways: either statically configured, static routes, or dynamically routing protocols. Those will be router updates sent by other routers that will update the current router's information. And we're going to be focusing on static routing in this course. The third course, we will get into dynamic routing protocols and kind of how they function. So the last way that a route gets in the routing table is the default route, which will specify basically the next hop router to use if nothing else matches. And that's typically denoted with a /0 prefix, and it basically just states, hey, all else fails, send this there. So how do packets get forwarded? This forwarding methodology is also important to understand for the exam. So again, a packet forwarding decision process tree is made up of these 5 steps, essentially. The data link frame with a encapsulated IP packet arrives on the ingress interface, so it's coming into the router. The router will examine the destination. It will decapsulate the frame, pull the IP packet datagram out of the frame. It will examine the destination IP address in the packet header, and it will look at the routing table. The router will find the longest matching prefix in the routing table. The router will encapsulate the packet in a new data link frame and then forward it out the appropriate egress interface. The destination could be a device connected to the network, or could also be a next hop router. It kind of just depends. If there is no matching route and there is no default route set, the packet will be dropped. So again, if there is no exit interface that was identified by the longest match and there was no default route, then the destination is undeliverable. Packets get dropped. So it's interesting because after the router has determined the best path, it could do the appropriate action. Well, it should do the appropriate action. It should forward the packet to a device on a directly connected network. That is always going to be the highest priority. The best route will always be the most trustworthy, and directly connected routes are normally viewed as the most trustworthy. And again, it has to encapsulate the IP packet into an Ethernet frame, and the router will determine the appropriate MAC address to send it to. Because again, IPs operate at layer 3, MAC addresses operate at layer 2, and it needs to be broken down into layer 1 bits to be sent over a wire. So the IP packet has to go to a frame, that frame has to go to bits, and then forwarded. It has to be forwarded out a physical interface, which the MAC actually controls. That is why the IP packet has to be encapsulated into a frame. and then again the frame into bits. The frame will be switched at each hop, because again the frame will just be the destination MAC address of the next hop. So if there's multiple routers along a path, the frame will be replaced by the next destination hop each router, or at each hop. So if there is a next hop router, instead of it being directly connected, the route entry will indicate the destination IP address of the remote network and where to send it. The packet will be then forwarded to the next hop router, and the next hop router address is indicated in the entry table. It will say send to this IP address. It will then typically find a MAC address, maybe using ARP, maybe using ICMPv6 neighbor discovery for IPv6, and then it will use that information to figure out what the MAC address is for the next hop, and then it will then send to that next hop. The difference is that the router will search for the IP address of the next hop router in the ARP table or its neighbor cache instead of the destination IP address of the next packet. Again, here you need to understand, because a directly connected network, the MAC addresses should already be known because they're directly connected. With the next hop, they are not always directly connected, thus you need to figure out the appropriate MAC address to send it through. This process will vary for the other types of layer 2 networks, because we talked about Ethernet frames, and that is just one of the layer 2 networks. And again, if there is no match in the routing table, the packet will be dropped. The primary responsibility of packet forwarding function is to encapsulate the packets in the appropriate data link frame type. Again, we talked about Ethernet, but that's not the only one. Data link frame format could be a serial point-to-point, a high-level data link layer like HDLC, could be frame relay, could be others. Realistically, most of what we learn about will be Ethernet frames, but they are not the only ones. Other packet forwarding mechanisms are out there. So again, the primary responsibility of the packet forwarding function is to encapsulate the appropriate frame types and then to forward those frames using the appropriate mechanisms. The three main mechanisms are process switching, fast switching, and Cisco Express forwarding, which we've discussed these in great detail when we talked about switching, but these also happen for packets. So again, process switching is an older packet forwarding mechanism that's still available on most Cisco routers. Basically, when a router receives a packet on an appropriate interface, it is forwarded to the control plane where the CPU will match the destination address to an entry in the routing table, and then it will determine the appropriate exit or egress interface and then forward it to that interface. It is important to understand that the router does this for every single packet, even if the destination is on the same stream of a packet. The crappy part with that is CPU intensive. So with fast switching, it's also an older forwarding mechanism which was a successor to process switching. Fast switching will use a fast switch cache to store next hop information, so it doesn't always have to go to the control plane and the processor. So if the packet is known and in the fast forward cache, it doesn't have to go to the control plane or processor. If it's not in the cache, then the packet would have to be sent to the control plane, processed. Information would then be stored in the cache, and then it would go at the appropriate egress interface port. Well, all of that was kind of changed with the Cisco Express Forwarding, CEF. This is the most recent and is currently the default iOS packet forwarding mechanism for Cisco devices. CEF will build a forwarding information base, a fib, and an adjacency table. The table entries are not packet triggered like fast switching, but change triggered, such as when something is changed in the network topology, then the information will be updated. When a network has converged, the fib and adjacency tables will contain all the appropriate information that the router will need to consider the appropriate next hop or forwarding decision. Questions, concerns, please reach out. Thank you.